When the problem statement describes some random process, or it's guaranteed that the input to our program will be generated randomly, uniformly at random, it's obvious then that we should use some properties of that. It's less obvious that we should use randomized algorithms where the statement is normal, and only in the solution we need to use rand or maybe random shuffle, maybe hashing, something like that. We will see some examples of it today. A quick warm-up problem for you is, if you toss a coin repeatedly till you get tails for the first time, how many times on average will you toss this coin? To answer this question, we can, for example, draw a decision tree, a tree that shows what can possibly happen. If first we get tails, then we win immediately and the number of tosses was 1, and so on. Then we can sum up probabilities of different answers to get some, this is called expected value, and it turns out to be 2. But today it is not important for us. For us, realistic pessimistic case is important. Can we say that 10 tosses should be enough? Or can we say that 30 tosses should be enough? We don't care about the average case. We just want to pass tests in some competitive programming, let's say, problem, and we want to do it with big enough probability. If we have some process or event that has 50% probability to happen, then after repeating it 20 times, we have very high probability that at least once it will happen, because it will not happen each time with probability half, and that power 20 is around 1 over million, over 10 to the 6, which is a very small probability of failure every time. If you raise that to 30, if you try 30 times, you can be almost certain that at least once you get a success, which here is to get a tail. And that's the idea behind a lot of randomized algorithms, that we repeat some process, maybe complicated one, each time we have some probability that we succeed, and by repeating that like 30, maybe 100 times, we are almost certain that we succeed in total, because if the probability of failure every time is 1 over million, then the probability of success, at least once, is 1 minus that 1 over million, which is close to 1. You should remember that there might be 100 tests in a problem, but still, with this probability of failure, you should pass all the tests. Consider a problem where there is a hidden integer x and your task is to guess it. What happens is, an interactor program repeatedly either gives you a number x with probability 50%, or otherwise it will give you some number smaller than x. Let's assume everything is positive, and x is from 2 to a billion. When should you stop the interactor and say, hey, I know what is x, I'm guessing that this is x? You should be almost certain. You can never be certain, because even if you get a sequence of numbers like 2, 7, 5, 7, 7, 7, 7, 7, and maybe 100 sevens, and some smaller numbers, still it is possible that the interactor, a lot of time, what happened is with probability 50% number smaller than x was given to you, and interactor chose a number 7. And this statement is quite vague. An important question is whether this smaller than x number is chosen at random as well or not. If yes, if let's say here maybe x is 10, but if in the other case where smaller number is given and the interactor generates a random number from 1 to x minus 1, then the probability that so many times 7 was given is very, very small. But otherwise, if interactor can be malicious and choose that smaller number, so let's say every time it just chooses x minus 2, because x is 9, then you will not be certain after, before maybe 30 tries or 20 tries. Because the probability that every time smaller number happened is 1/2 power k, where k is the number of tries. And after, let's say, 30 tries, I can say at least once I got that number x, so I can just print the maximum in a sequence. And there can be some heuristics. If we are guaranteed that x is at least, say, 4, and for this smaller number, generator, interactor, not a generator, will give us a random number from 1 to x minus 1, then already after seeing the same number a lot of times, we can say, and this is maximum so far, we can say, okay, I'm sure already. And maybe less than 20 or 30 tries is enough to get probability of success very close to 1. In some harder problems, you will need some heuristics like that, extra ifs. Finally, let's see a real problem from competitive programming, where the statement also doesn't mention anything about a random process, but it has an unusual condition. We're given n points in 2 dimensions, each with coordinates x and y. You should find a line that passes through the maximum possible number of those points. So a lot of points can be collinear. You should find such a line that it will contain as many points as possible. And we are given information that the answer is at least n over 4. And when you are given such an info about answer that it's big, you should always remember that that might mean randomized algorithm. The naive brute force here can take every pair of points, and for this pair of points I imagine a line and I count points that belong on this line. For those 2 points I would consider this line, count the points. That in total works in O of n cubic, because for each of n square pairs I go through all other points. Then something faster would be to, for every point, sort other points by angle with respect to this one, and then do something smart with this order. But because the answer is big, a randomized algorithm works that will say, let me take a random pair of points, say this one and this one, consider this line, count all the points, and repeat that 50 times, or maybe 200 times. And the thing is, because the answer is big, the probability that we will get the first point as one of those points in the optimal answer is at least 1 over 4, and the second point the same, so this is 1 over 16. This is probability of success, at least that. So probability of failure is 15 over 16, and this power, let's say 100, should be quite small. Maybe we need 200, 300, that of course depends on the constant. You can put that into calculator or Python to figure out. And if you get that to be around, say, 0.0001, you're good. You can implement this solution. An alternative approach here is to like 20 times, maybe 50 times, take a random point, sort everything else by angle, and assuming that this point belongs to the answer, you will get that optimal answer. And if you repeat that for 50 random points, you have high probability of winning. Winning means finding that real optimal answer. So this 1/4 times 1/4, which is 1/16th, is the probability that if we take a random pair of points, they both belong to optimal line, because there is some optimal line that contains the maximum possible number of points, and because we know that there are at least n over 4 points on them, the probability of generating a random point that belongs to that is around 1/4 or more. And this will be probability that both work. Of course, to generate a random point, you just generate its index. Let I be a random integer from 0 to n minus 1, and then you say this is the point. J will be another index from 0 to n minus 1. If you get 2 same indices, then just repeat the process. You can also add some speedups that might be useful for small n. That is, if you already checked this pair ij, then skip and generate another pair ij. Links in the description contain some Codeforces blogs that talk about randomized algorithms or hashing, for example, and in one of them you will find this GCD, or actually GHD was the original name, Codeforces problem, where given a sequence of numbers, we should find maximum possible greatest common divisor of a subset of those numbers, and this subset should contain at least n½ numbers. That is, for a long sequence, we should take at least half of them, can be neighboring, can be not neighboring, compute GCD of them, and among those possibilities, find the maximum possible GCD. And this problem is very similar to the previous one, because again, we have some condition about some set of things being at least n over something. And now if you take a random number or two random numbers, you have very high probability that they will belong to the answer. The intended solution here is to, like 20-30 times, take a random number and consider all its divisors. Because if you know that this number is in that subset, optimal subset, then one of its divisors will be the greatest common divisor of a set. And when you have a candidate for an answer, you can just linearly go through all the numbers and see how many are multiplies of your candidate. If this is 14, then I want to check numbers 1, 2, 7, and 14 as possible GCD. And if I notice that at least n over 2 numbers are divisible by 2, then I know this is a candidate for the answer. Let's get back to guessing a hidden thing, and here it is a string with characters ACTG. What you can do is ask if some string that you choose is a prefix of that hidden string s. And let's also say that we know the length of this string s, that is n. N is length of s. And we want to use as few queries as possible. This time the statement doesn't have anything about the least number of something or a random process, and still we will be able to use a randomized algorithm. Well, let's start with a brute force. A naive thing to do is to ask if a is a prefix of string s. Let's say that no, it isn't. Then try c, then try t, and so on. Finally, when you have a match, continue with that. After t, if I add a, is that a prefix? No? Try tc. Is that a prefix? Yes. Then try a, try something, and so on. Maybe this doesn't work, then tcac, and continue with that. The number of queries that we use is 4 times n, and we want to speed this up. Because let's say the statement said that n is up to 100,000, and the limit is around 250,000. What is a bad case for our algorithm? If we every time try characters in order A, C, T, G, then if character that is really in string S is G, then we'll use 4 queries to find that out. But if it's A, it's better. We could change this order, but for every order that you choose, there will be some counter test. But what you should do, assuming that an interactor isn't malicious, that there is really a hidden string and interactor doesn't change that while you ask queries, then you can random shuffle the order of characters ACTG, the order in which you will ask query about the next character, because this is basically what you do. You start with first character of S, second character of S, and so on, and you try to guess each next one of them. It isn't correct to just say that I once random shuffle order, I get TACG or something else, and then still a string in the input, like hidden input, GGGGG, would be a counter test. What you should do is random shuffle this order every time for every character. So when you have a hidden string S, to guess the first character, you random shuffle ACTG, and in this order ask, then random shuffle it again to ask about second letter, and so on. Now, because with probability 1/4 you will guess for the first with the first try, then maybe second try, third, and fourth. The average of that is 2.5. This is the average number of queries you need for one character. And from this we get that the average number of queries that we ask is 2.5 times n, which is too big. Because if this is the limit, and on average we get exactly that, then sometimes we will exceed it. So you can now pause for a moment and think about an easy fix. And this easy fix is not to ask about the fourth character. If you failed with T, A, and C, then you know that this character must be G. So instead of asking this last fourth query to know a letter. You already know it. So instead of 2.5, you have 2.25. And 2.25 times n is good enough. Later, we will think how far actually we can go, how far away we can be from that. If we see that the average number of queries that we ask is 225,000, then can we exceed 250,000? Likely not, but can we be sure? Something that is related to this distance from average case is called variance, but fortunately we don't have to really understand it and dive into formulas in order to solve most of the problems. Example problem is, or maybe a process that we should consider is, if you toss a coin 1 million times, how many tails will you get? Of course, it will be around 500,000, because we assume a fair coin that has 50% probability to give you tails. But can you get 600,000? And if you, for example, toss 10 times, then how likely you are to get 0 tails? And this probability is 1/2 power 10, but how likely you are to get exactly 5? Here there is some math formula for that, which is 10 choose 5, this is binomial coefficient, divided by 2 power 10. I don't know this value exactly, I would guess it's around 1/3, maybe 1/4, 1/5, something like that. There are 11 possibilities, and this is the most likely of them, because most often we are exactly in the middle. But how far away we can get realistically? Not with probability 1/10 to 100. Just what can happen during a contest when we submit and it will be tested on 100 tests. Let's see results of some simulation of that. And here on the left you can see a program where I chose n to be 1 million, and 1 million times if round modulo 2, which means with probability 50%, increase the counter by 1, and then print this counter and also its distance, absolute value of difference, counter minus n/2. On the right you can see results where indeed the counter is around 500,000, but the second value, the distance from 500,000, is quite small. And what you should remember is, for this random process with 50% probability, that average distance, also realistic distance that you should expect, is around square root of n. And that means 2 times square root of n can happen, 3 times square root of n can happen, but 10 times square root of n is not very likely. And if you have this value in complexity, or you will ask queries till something like that happens, you should expect that it will be around that. And those numbers on the left, on the right, experimentally confirm that. During a contest, if you have some more complicated process, you shouldn't dive into formulas, as I said. What you should do is just implement that and run your machine to see what happens. Run this process 10 times like I did, or maybe 1000 times, and tell your program to find that maximum distance. It should be here a few thousand. In some other problem, like this ACTG, you can also see how far away you will get from 2.25 times n. Last advice for today is not to use a fixed random seed, or not to have a seed at all, because then it's 0 by default, in Codeforces or Topcoder contests. So do not use that, or that is example in C++. You can use the second one, and the third version here is perfect. So this is okay, but this is the best. Why is that? Because there are hacks. Both in Codeforces and Topcoder, somebody can open your solution and can try to hack it. If you have a fixed seed, they can, for example, rewrite your solution, see what random numbers you use, and construct a malicious test that works exactly against your solution, for which, even though your probability of losing is like 1/1000, but this test is exactly constructed so that, for example, hashes will collide, or you will never get this result of your process that you would want. Sometimes constructing such a test is very hard, but sometimes it's easy, and instead of worrying if it's possible or not, just do not use a fixed seed. That being said, a fixed seed is better for your own testing, because you can get some answer again. If you see a counter test and you run your program again, you get something else, that's bad. It's better to have a deterministic program. And then I recommend on your computer, while you experiment with something, use a fixed seed, or just don't put strand, which will use seed 0 or 1, I don't remember. But when you submit, at least use the second version, time null, that as random seed it chooses the current second. There can be some very smart hacker that would figure out what can be a current second, well, like with custom invocation in Codeforces, and can try to predict that. So the even better thing is the last possibility that uses nanoseconds or milliseconds, something like that, that is impossible to predict exactly. And this is what I would use in a problem in Codeforces or Topcoder where there is some randomization. And remember, for Codeforces, that rand returns only numbers up to 30,000 in C++, because Codeforces uses a different architecture. I think it's 32 bits, and because of that it's smaller. You can use always on your machine rand max in C++. You can print that to see what it is in your system. It should be around billion or 2 billion, not only 30,000. And if you want in C++ in Codeforces to use a random number from 1 to around billion, then use piece of code similar to the one below. It is not perfect, just because this randomization in Codeforces is so weaker, but here I generate two random numbers, each up to 30,000, and then I combine them into one up to 1 million. I use long so that it wouldn't overflow even locally, where locally rand max is much bigger. I will record and upload the second part of this lecture in a few days, so make sure to subscribe and turn on notifications not to miss that. Plus, it helps the channel, so thanks a lot for that. See ya!